Good day everyone, and welcome. Today, we delve into the fascinating world of large language models with our presentation on Lora, low-rank adaptation of large language models. This groundbreaking research addresses the challenge of efficiently fine-tuning these models for multiple applications without compromising on quality. Stay tuned as we unravel the intricacies of Lora, a novel strategy that promises to revolutionize the way we adapt and deploy these models. Let's embark on this journey of discovery together. The challenge we face is adapting large-scale, pre-trained language models like GPT-3 to multiple downstream applications. Existing methods have their drawbacks. They introduce inference latency, reduce the model's usable sequence length, and often fail to match the performance of fine-tuning baselines. Now let's delve into the problem statement. Current fine-tuning methods create a new model with as many parameters as the original model. This is not only inefficient, but also poses significant deployment challenges. Imagine having to store and deploy numerous independent instances of fine-tuned models. This becomes especially daunting, if not impossible, when dealing with large models like GPT-3, which boasts a staggering 175 billion trainable parameters. In our research, we aim to address these issues and propose a more efficient and feasible solution. Our research introduces a novel method called Lora, which stands for low-rank adaptation. This strategy is efficient in terms of both computation and memory. It uses a low-rank representation to encode changes in model parameters, which is a significant step forward in the field. What sets Lora apart is its ability to maintain high model quality without introducing inference latency or reducing input sequence length. This is a crucial aspect, as it allows for the model to operate efficiently without compromising on performance. Furthermore, Lora has a unique feature that allows for quick task switching when deployed as a service. It achieves this by sharing the vast majority of the model parameters. This means that it can adapt to different tasks swiftly, making it a versatile tool in the realm of language models. In essence, Lora is a promising strategy that combines efficiency, quality, and versatility, paving the way for future advancements in the field. Our research has yielded several key highlights. Firstly, our proposed strategy, Lora, has the potential to be combined with other efficient adaptation methods. This could lead to orthogonal improvements, enhancing the overall efficiency of language models. Secondly, we've discovered that the ranked efficiency of increment W implies that W could also be ranked efficient. This intriguing finding opens up new avenues for future research. Lastly, our results show that fine-tuning significantly outperforms few-shot learning on GPT-3, a crucial insight for the development of future language models. As we delve into the world of large-scale models, we encounter a significant challenge. Current methods of fine-tuning these models result in a new model with an equal number of parameters as the original. This leads to inefficiency and presents considerable deployment challenges. This issue becomes particularly critical when we consider colossal models like GPT-3, which boasts a staggering 175 billion trainable parameters. Now let's take a look at this figure. It shows the validation accuracy of GPT 3175B against the number of trainable parameters of several adaptation methods on WikiSQL and MNLI matched. What stands out here is the superior scalability and task performance of Lora compared to other adaptation methods. This illustrates the potential of Lora in addressing the challenges we've just discussed. Existing methods for adapting large-scale, pre-trained language models to multiple downstream applications have their limitations. They either adapt some parameters or learn external modules for new tasks, which can introduce inference latency or reduce the model's usable sequence length. Furthermore, These methods often fail to match the performance of full fine-tuning, creating a trade-off between efficiency and model quality. Our paper proposes a solution to these challenges, a low-rank representation to encode the change in parameters, denoted as increment phi. This approach is both compute and memory efficient, significantly boosting operational efficiency when deployed. It allows us to adapt large models like GPT-3 to various tasks without the need for extensive storage or computational resources. This is a significant step forward in making these powerful models more accessible and practical for a wider range of applications. Our research is primarily focused on the field of language modeling, where we aim to maximize conditional probabilities given a task-specific prompt. We take a pre-trained autoregressive language model and adapt it to various downstream conditional text generation tasks. These tasks include, but are not limited to, summarization, machine reading comprehension, and natural language to SQL. However, we face a significant challenge in this process. The full fine-tuning of the model for each downstream task results in a different set of parameters. If the pre-trained model is large, storing and deploying multiple instances of fine-tuned models becomes a daunting task. Our paper proposes a more parameter-efficient approach to tackle this issue. We'll delve into the specifics of this approach as we progress through the presentation. We introduce Lora, a novel and efficient adaptation strategy for large-scale models. Unlike other methods, Lora does not introduce inference latency or reduce input sequence length. It leverages a low-rank representation, optimizing both compute and memory efficiency. One of the key advantages of Lora is its ability to enable quick task switching. It achieves this by sharing model parameters, which is a significant improvement over hosting independent instances for different tasks. Importantly, the principles behind Lora are not limited to transformer language models. They can be applied to any neural networks with dense layers, making it a versatile tool in the field of machine learning. In our research, we conducted a rigorous experiment with GPT-3, a model with a staggering 175 billion parameters. We compared its performance against a fine-tuning baseline across 3 distinct datasets. Our investigation also delved into the performance of various adaptation approaches, particularly in scenarios with limited data. Interestingly, we observed a significant performance drop when we used more than 256 special tokens for prefix embedding tuning, or more than 32 special tokens for prefix layer tuning. This observation aligns with similar findings from other studies. In essence, our research aims to understand the behavior of large-scale models like GPT-3 under different conditions, and to explore efficient ways to adapt these models for various tasks. Our research introduces several key improvements and innovations. Firstly, our proposed strategy, Lora, matches or even exceeds the fine-tuning baseline across all datasets. This is achieved without introducing inference latency or reducing the sequence length, which are common issues in other methods. Moreover, Lora is more parameter efficient, making it a practical solution for storage and deployment, especially when dealing with large models like GPT-3. This efficiency does not compromise the quality of the model, but rather enhances it. Additionally, Lora's design allows it to be combined with other efficient adaptation methods. This opens up the possibility for orthogonal improvements, further enhancing the performance and efficiency of the model. In essence, our research presents a promising direction for the future of language model fine-tuning, offering a balance between efficiency and performance. Let's delve into the key results of our research. The illustration here showcases the Lora reparametrization method. The beauty of this method lies in its efficiency. We only train matrices A and B, making it both compute and memory efficient. Now, onto the performance of Lora. It matches or even surpasses the fine-tuning baseline across all datasets we tested. However, it's important to note that we observed a significant performance drop when using more than 256 special tokens for prefix embedding tuning, or more than 32 special tokens for prefix layer tuning. Interestingly, fine-tuning significantly outperforms few-shot learning on GPT-3. This highlights the potential of Lora as an efficient adaptation strategy for large language models. Our key results highlight the compatibility of Lora. It has the potential to be combined with other efficient adaptation methods, leading to orthogonal improvements. However, we also noticed an interesting phenomenon. As the number of special tokens increases, performance tends to drop. This suggests that the input distribution is shifting away from the pre-training data distribution. Another intriguing finding is the rank deficiency of increment W. This suggests that W could also be rank deficient, opening up new avenues for future research. Lastly, in our ablation studies, we explored the selection of weight matrices for applying Lora. We believe there could be more principled ways to make this selection, and this is an area we're excited to delve deeper into. Our research addresses the significant challenge of fine-tuning large-scale, pre-trained language models. We've introduced Lora, an efficient adaptation strategy that uses a low-rank representation to encode changes in parameters. This approach not only maintains high model quality, but also allows for quick task switching when deployed as a service, making it a practical solution for real-world applications. Furthermore, the principles we've proposed aren't limited to language models. They can be applied to any neural networks with dense layers, broadening the potential impact of our work.